right. How are we all doing? Okay. How are we feeling about, I don't know, stuff in this class? Okay, so far okay? Alright, it's not too bad. Okay, so what we've seen so far is, once we got into hypothesis testing, so all of this is kind of built off of understanding, sampling distributions. And we talked about hypothesis testing for t-tests, basically comparing two groups, the means of two groups. And then we also looked at hypothesis testing for categorical variables. So that would be the chi-squared test, whether it was a relationship between two variables or whether a certain model that we had in mind fits the distribution given for categorical variables. And today, this is almost like an extension of the t-test, except but we can now compare more than two groups. Okay, so with a t-test, we would compare. It's used. Compare the means of two groups. And when you just do a straight t-test, it's two independent groups. So if it's paired, then we have the paired t-test. But otherwise, we compare the means of two groups. But what if we had more than two groups? Okay. Well, let's just make up some example here. Okay. This I will take from the book, and this apparently some farmers, they want to see if they grow organic corn, if different kinds of things would affect how much how the corn grows. Okay, so they're measuring the weight of the ears of corn, and they just want to see the different treatments affect this. Okay, so they subjected it to, there's 5 different treatments, and it goes into, I guess there's nematodes, wasps, and bacteria and things like that. And this is basically the summary of the data. Okay, so we have treatment 1, 2, 3, 4, and 5, and then and each of these has a mean. So there's measurements within each of these groups, but they can just be summarized with the mean and standard deviation. And in each of these groups, we had 12, okay? Now, the groups don't have to be of equal size, but they happen to be of equal size here. Okay, so the question is, do any of the treatments basically have an effect on the yield of corn, okay? I guess the weight of your just close the door here. So how would you guys suggest we do this? Try to answer this question here. So, with the knowledge that you guys have so far, maybe you would say, let's just do some t-tests. Okay, we'll just take two groups at a time, and we'll do some t-tests. Okay, and this is what people did in the beginning because they thought that would be fun. Okay, so and then we run into, so if we were to do that, so can we just do a bunch of t-tests, okay? So then we could, and if we wanted to do this, we could compare to group 1 versus group 2, group 1 versus group 3, 1 versus 4, 1 versus 5, okay? And then we have 2 versus 3, 2 versus 4, 2 versus 5, and 3 versus 4, 3 versus 5, and 4 versus 5. Is that right? Did I miss any? So I think there's a total of 10 tests for us to compare. Just a bunch of t-tests. Okay, so I mean it would be a lot of work, but so we would have Can anyone see any kind of problem with doing a bunch 10 t-tests? Or would this be totally okay?
It's not comparing all the data like collectively?
Okay, so I mean, yeah, we're not doing everything collectively, but okay, so that's an issue.
It's really tedious. It's really tedious.
I mean, the tedious part is not so much of an issue. I mean, to do it by hand, it would become really tedious. But when you've got a computer, you can just throw it at it, and it'll do 10 t-tests quickly for you, and it's not too bad. Okay. So yeah, it's a little bit tedious. That's true. But this is not just a small issue, minor issue. And then we're not looking at the data as a whole. The data is not seen as a whole. That's also a little bit of an issue, okay? You know, not a major issue though, okay? The biggest issue here is what does it mean to choose an alpha of 5%? So let's say you chose what is the probability of a type 1 error? Huh? So alpha is the probability of a type 1 error, right? So that means, and a type 1 error is again, what is it?
Rejecting the null when it's true.
Yeah, rejecting the null when the null is actually true. Okay. So if we choose alpha to be 5%, we're running kind of a 5% risk every time we do a t-test. Okay. So what's the probability? And maybe this is the answer is a little bit, is not quite this, but what's the probability of running through 10 tests and emerging unscathed in terms of not ever committing a type 1 error? so if alpha is 5%, what's the probability of not committing a type 1 error? 95%. And then what would be the probability of doing 10 tests and not committing a type 1 error in any of those 10 tests? So let me just write this. Okay, so probability of not committing a type 1 error would then be 0.95. And so probability of conducting 10 tests and not making a type 1 error
Point 598.
okay, 0.598.
60.
Okay, so about 60%, okay? And it's technically not this, because this assumes each test is independent of one another and you're using the same data, so they're not really independent, okay? So not really, because the tests are not truly independent, okay? But we can see how the probability of type 1 error has now ballooned from 5%, choosing alpha 5%, now it's about 40%. Now we run about a 40% risk of committing a type 1 error. Okay, so risk of a type 1 error. Okay? When you do this many t-tests, yeah.
So what would our null hypothesis be in this situation?
Okay,
if
so-
we're doing just a bunch of individual t-tests.
So if we do 10 t-tests, each one would be, the null is group 1 and group 2 have the same mean, alternative, they have different means. The null here is that 1 and 3 have the same mean, the alternative is that they're different. 2 and 5 have the same mean, and the alternative is that they're different. So when we do a whole bunch of t-tests, our risk probability of a type 1 error is now a lot greater, okay? So you might choose alpha 5%, but then when you do a whole bunch of t-tests, every time you run a t-test, basically you're accepting a 5% risk of a type 1 error, but if you do this a whole bunch of times, eventually you're bound to make a type 1 error, okay? And so, so this is part of the problem with committing of running a whole bunch of t-tests, okay? And it's a problem with a long history in statistics, and it's just called the problem of multiple comparisons. And it's hard to do to compare a whole bunch of things for this reason. And so people have suggested all sorts of different solutions to this thing, and they say, okay, well, if you want an overall risk of 5%, then you have to choose alpha to be, do 5% divided by 10 tests, and choose an alpha of basically 1/2 of 1%. But then when you do that, then your beta, the probability of a type 2 error, skyrockets. Okay, so there's all sorts of things. If you take a class on ANOVA specifically, which is this chapter, they'll talk about this quite a bit. Okay, so one solution is to do something called ANOVA. Okay, and ANOVA comes from analysis of variance. we are going to learn just the most basic form of ANOVA, known as one-way ANOVA. Okay. This class, we're just gonna learn. I'll give just a brief explanation of what the other versions of ANOVA do. The book goes into a little bit more detail on the analysis for two-way ANOVA and blocked design ANOVA and things of that sort. But we'll just cover the most basic form of ANOVA. And again, just like there will be entire courses on one aspect of statistics, you can take entire courses on ANOVA, but we'll just get the treatment here. Okay. All right. So the approach with ANOVA is we look at the data collectively. Okay. And there's a little bit of a trade-off when we look at the data collectively as a whole. Okay. And we just pile. In this case, if we had 5 different groups, we would set up 2 hypotheses. Okay. If there's 5 groups, or whatever, the null hypothesis is that the mean of all the groups' respective populations of all the groups' respective populations are equal. That sounds okay. Or in other words, symbolically, we would write mu1 is equal to mu2 equal to mu3, whatever, to the last mu that you have. And the alternative is at least one of the means is different. And symbolically, we just write the same thing because we are not specifying which one. So we say at least one is different. Okay, so practically all ANOVA analyses are non-directional. Okay, only if you have 2 groups, then you can have directional analysis, ANOVA. But if you've got more than 2 groups, they're all non-directional. Okay, so whenever you have more than 2 groups, non-directional test. Okay, so ANOVA comes from the term analysis of variance. So let's talk about what variance is in the first place. Okay. All right. So what is? somebody want to volunteer an explanation or definition of variance?
When two things are not equal?
Okay, so just kind of a more colloquial definition from life, where things aren't the same, right? So, you know, everything in life is different, and so that is variance, indeed. I was thinking more in terms of statistics, okay? So maybe variance, we think of this, this is the number you get before you take the square root, right? To get the standard deviation. You take the square root of variance, you get the standard deviation. So, so variance would be basically s squared, and this would be the sum of y minus y bar quantity squared over n minus 1. Is that alright? So if we just look at this piece right here, this y minus y bar squared, okay? Let's just look at that. This is a value that we calculate for each point, and this is basically the squared distance from the mean. So if I have a data set, and let's say I've got a dot here and a dot here and okay. So my mean, so my data set would be 4, 5, 7, 9, 10. Okay, so my mean here would be 7, and if we were talking about variance, basically this dotted line represents my mean, and the variance is basically a measure from this point to this point, and then I'm squaring it, okay? And then I take the distance from this point to this point, and I square it, and I do the same for this point, and also this point, okay? And then so we say, okay, all of these, and also this one is at the mean, so it contributes 0 towards the variance. But basically, what we're saying here is we've got 5 data points. The mean is 7, but all of the data points are not equal to 7. Some are larger and some are smaller than 7. So we come up with this term called the variance, and this would be the sum of each of these things. So 4 is 3 units from 7, and we square that. 5 is 2 units from 7, and we square that. 7 is 0 units. 9 is 2 units, and 10 is 3 units. Okay, and then we add all of these up, and we divide by 4. But anyway, this is kind of the idea behind variance. All right, is this okay? All right. So keep that in mind, and let's talk about ANOVA. Okay, so here we're going to look at a very simple example for one-way ANOVA. And let's look at some data here. Okay, so here this is some made-up numbers here that the book made up, but it's based on I guess we gave some lambs different diets, and we want to see how much of weight they gained. So we've got 3 different diets. We've got diet 1, diet 2, and diet 3. And the numbers are 8, 16, and 19. Diet 1. Diet 2, 9, 16, 21, 11, 18. 15, 10, 17, and 6. So overall, okay, and then the summary statistics. So this is, we've got the count for each group, the mean of each group, and the standard deviation of each group, which is 3, 11, and 4.359. Here we have 5. The mean is 15, 4.95. And here we've got 12 and 4.967. Okay, so let me, so this is what we're doing here, okay? Just imagine I put all of these numbers, so how many numbers do I have total? I have a total of 12 numbers. Just say I put all 12 numbers together, and if I graph them, okay? So let me see if I can do this. Okay, so if I just put all of these, 8, 9, 16, and 9, 16, 21, 11, 18, and then 15, 10, 17, and 6. Okay, so this would kind of be a dot plot of all 12 points together. And we could say, you know, what is the overall variance? Okay, what is the variance here? And we would say, oh, okay, well, we can figure this out. First, we got to figure out the mean. Okay, and we could add up all 12 numbers and divide by 12. And if we did that, the mean that we would get is 13. Okay, so if we did the overall mean of all of these numbers would be 13. Okay, and so this is known as the grand mean, and we distinguish it by y bar bar. Okay, the y double bar. And this is the mean of all 12 points. Okay, grand mean of all 12 points. Okay, we'll get into the formulas for all of this. What ANOVA is going to do is it's going to say, okay, well, that's fine and dandy. Here's the mean of all 12 of these points is 13, and at this point, all we can say is some lambs gain more weight than others. Okay, some lambs gain 21 pounds, some lambs only gain 6 pounds, and it's just lambs are different from one another. They gain different amounts of weight. Okay, what we want to know is, okay, sure, you can tell me that lambs gain different amounts of weights. I'll buy that. But what I want to know is, are the diets, the different diets, do that play a factor into the reason why lambs gain a different amount of weight? Okay, so basically I'm going to take these 12 points and I'm going to break them out into different layers. Okay, so I wish I could do something, go poof and you'll see the dots drop out to different spots. But I'm going to just have to say, okay, let me just show where the dots are for diet 1. So this is this number. So this would represent diet 1, and diet 1 I've got a dot at 8, 9, 8, 16, and 9. And then for diet 2, I've got 9, 16, 21, 11, and 18. And then for diet 3, I'm at 15, 10, 17, 6. Okay, so I've tried to split out the 12 points into the different diet groups. Is this clear what's happening here? Okay, and so what we want to know is, okay, then are the diets, do they produce different weights from each other? Do they produce different lamb weight gains from one another? Okay, so we can say, well, what was the average of diet 1? Okay, so if we look at diet 1, the mean weight, so if I add these 3 up and I divide by 3, I would get 11. Okay, so 8 plus 16 plus 9 adds up to 33. 33 divided by 3 gives me 11. So this is the mean of diet 1. And if I look at diet 2, the mean of diet 2 is 15, right there. And the mean of diet 3 is 12. Okay. So what we're seeing is that the grand mean is 13. Diet 1 produces a mean that's 1 pound less than the grand mean. And diet 2 produces a mean that's 2 pounds more than the grand mean. And diet 3 produces a mean that's what did I say? Diet 1 produces a mean that's 2 pounds less than the grand mean. Here we're 2 pounds greater than the grand mean, and this is 1 pound less than the grand mean. Okay, can we see that? So what we want to know is, okay, when we look at the individual averages of each of these diets, it seems like the diets do produce different means that are different from each other. 11 is not the same as 15, and it's not the same as 12. Okay, so yeah, there's differences between the diets. The question is, are the differences that we see between the means and the diets, is it because the diets are actually different? Or is it possible that just because lambs overall in life are different from one another, that just by random chance, I happened to select 3 lambs that were on diet 1 that produced a mean that was lower, and 5 lambs that were on diet 2 that produced a mean that was higher, and 4 lambs on diet 3 that produced a mean that was somewhere down here also. Okay, so we want to know, are the differences between the diets, is there something truly different about the diets? Or is it just possible that, we observe these differences because lambs are different. Whenever you pick a random sample of lambs, you're going to get different lambs, and you're going to get different averages. Okay? So, basically what we're going to do is we're going to try to measure how different our observations are from what we expected. So, so all of these, we're comparing what we observed versus what we expected, and we're taking that difference and we're comparing it to like a standard error, right? the same concept here, except everything is always a little bit different. So we're going to try to come up with some way to measure how different our observations are from what we expected. So if we expected all 3 diets to produce the same mean, we would expect everything to be around 13 pounds, okay? To produce a mean around 13 pounds. We see something that's a little bit different. So that's our observed difference. We're also going to compare that basically to the overall, quote, standard error. It's not the standard error, but a concept like that where it's, now we're just going to measure the overall variation that exists within each diet. So we're going to break it. When we do ANOVA, we break up the variance into 2 components. Okay, so with ANOVA, break the total variance into 2 parts. Okay, one part is variation that can be attributed to the different groups. Or attributed to different groups. And then variation attributed to basically differences between individuals within a group. Okay, so the groups themselves might be different or are different from one another, and within each group, the individuals are different from one another. Does that make sense? Okay, so just looking at this, do you think the diets produce means that are different, or could any difference that we observe just be attributed to the fact that lambs are different?
I think they're too different to be chimps.
Okay, so you think that the fact that this mean here and this mean is over here and this mean is over here, it's too different to be due to just chance?
Oh,
Or
I was looking more at the individual.
okay, yeah, not the individual. We're looking at. Well, I mean, we could look at the individuals, but yeah, we're looking at the different means, the means of the different groups. Because what was the null hypothesis for ANOVA? It's that the means are all the same, and then the alternative is that at least one of the means is different. So does it seem like we've got evidence that at least one of the means is different, or does it seem like the means could all be the same? Well, we'll look at we'll do the analysis here, okay? But to me it seems like, yeah, the means are different, but within each group there's so much variation between the individual lambs that if they are different, it could just be because the lambs themselves are different from one another, and not necessarily the diets. But we'll break this down, okay? So when we do ANOVA, we're going to create an ANOVA table, and we say there's the source of variation, and we say source is the variation that exists between the groups, and then the other source is the variation that exists within groups. And then we'll talk about the total. Then we have degrees of freedom. We'll get to that. And then as a way to break out the variation, we're going to talk about the sum of squares. Okay, sum of squares. So remember when we looked at just the kind of the root definition of variation, we saw y minus y bar quantity squared. Right? Okay, so the sum of squares between the groups is going to be the fact that this mean is different from the grand mean, and the fact that this mean is different from the grand mean, and the fact that this mean is different from the grand mean. Okay? So this is going to be, what we're going to do is we're going to do for each group, we're going to take the mean of that group and take its distance from the grand mean of that group, or the grand mean of all the data points. Okay, so this is the distance from the mean of each group to the grand mean. So we take that distance and then we square it, and we add them for across all the groups that we have. Oh, shoot, forgetting something. Okay. Sorry. So we take that distance and we square it, and then we have to multiply it by how many points were in that group. Okay. So there's 3 points here. So we're going to take this distance from the grand mean, take the square of that distance, and we're going to multiply it by 3 to kind of represent 1 for each point. So we multiply it by the size of each group. Okay, and then we add them across all groups. Distance from the mean of each group to the grand mean, multiply it by the size of the group. Sum across all groups. So that's the sum of squares between the groups. Do sum of squares within the groups. Okay, so within the groups, I would just take the distance from this dot to the mean of the group, and this dot to the mean of the group, and this dot to the mean of the group, and then I would take this dot to the mean of this group, and basically just take the distance from each point to the mean of its own group, square it, and add across all points in all groups, right? So I would take each individual point and subtract off the group mean and square it, and I would add across each point in a group minus the mean of its group okay, and then we square it squared do this for all points within a group and do it for all groups. So I'm going to have two sums, okay, do it for all for all points within a group and sum across all groups. Okay, so within a group, sum for all groups. Okay. I'm gonna get in trouble here. This part right here, let's think about what is the standard deviation S, okay, or if we do, if I take the formula for standard deviation and I square it, so if I drop off this, I would get y minus y bar squared over n minus 1, right? So this is just the standard deviation or the variance within a group. Okay? If I multiply both sides by n minus 1, then I would get n minus 1 is equal to this. Right? Can we see that? So the sum of y minus y bar squared within a group is equal, so the distance from here to here squared plus this to here squared plus that to that squared is equal to the standard deviation of the group squared times n minus 1. Can we see that? I hope I'm not losing anything here. Okay, so sometimes what you will see is that this thing, this quantity here, this chunk gets replaced with this because we see this piece and this is exactly the same. So sometimes, actually, and this is what the book shows, is that this is equal to n minus 1 times the standard deviation squared, summed across the different groups. Is that alright? If you hate me, it's okay, but I'm just trying to show where it's coming from. Because, well, I guess at the end of the day, you can just say, here's the formulas, and I'm just going to plug in numbers, and we're just going to go. And I guess that works, but I just want to show you where they're coming from. Okay? So again, the concept is the total variance is just, each of these dots are different from the grand mean. Okay, and we're going to break out that total variance into two parts. One is because the diets are different from one another, so we're taking the distance from each group's mean to the grand mean. And then the other part is that the individuals themselves within a group are different from each other, and that can be broken down into the dots to the group's mean. Okay, and that's where the between groups and the within groups variation comes from. Okay. All right, and so you can just whatever number you get here and whatever number you get here, you can just add those two together, and it turns out to be equal to the idea of total sum of squares being each individual point from the grand mean squared, and we add this for all points in all in each group. So basically, just summed across all the points. Okay, so if we did this for all 12 points, the distance each point to the grand mean, we would get the total sum of squares, and it can be broken down into these two parts. So sum of squares, we write sum of squares total is equal to sum of squares between plus sum of squares within. This table got a lot messier than I wanted it to be. And I'm sorry. Okay, so let's let me just erase all of this and rewrite it nice and pretty. So okay, so the degrees of freedom, let me go back to making this table. Degrees of freedom is the number of groups minus 1, or I is the number of groups. I minus 1. The total degrees of freedom is total number of points, number of all points, minus 1. And the book calls this n dot to signify that this is the definitive number of points for total. So that. And within groups is total number of points, number of all points, minus number of groups. Looks confusing, especially because we got I's and 1's, and depending on your font and handwriting, everything might look the same. Okay, so this was sum of squares between. So you have a formula for that somewhere in your notes. Sum of squares within. Okay. And so to come up with, to decide, so we break out the variance, the total sum of squares, into the part that can be attributed to the fact that the groups are different from one another, and then the fact that individuals within a group are different from one another. So that's sum of squares between, sum of squares within, and to make it work, we have to come up, use these things called mean squares. Okay, so mean squares is basically you take the sum of squares and you divide it by the degrees of freedom. So you do sum of squares between divided by degrees of freedom between. And this is sum of squares within divided by the degrees of freedom. We don't bother with mean squares for the total. And then we look at the F ratio, which is mean squares between divided by mean squares within. So it's a bunch of division here. So once you figure out the total sum of squares, then you do some division.
What does that mean?
Huh?
Oh, mean of squares?
Mean squares, yeah. of squares and you divide it by the degrees of freedom to get your mean squares. And then you take the ratio between the mean squares. And this compares basically the mean squares that's for the fact that the group means are different from the grand mean. And we compare that to the mean squares that the dots are different. The individual dots are different from the group's mean. Okay? And we want to know, is the fact that these group means, the fact that the group means are different from one another, is that large or small compared to the individual differences? And that's what we're doing here. So we get the F ratio, and this turns out to be, this is not mathematical statistics, but we use the F ratio and we look it up into the F distribution. Okay, so we've got the T distribution, chi-square distribution, and there's also the F distribution, named after Fisher, which and it's it was a big stats guy 100 years ago. And it comes from basically a ratio of two T distributions, and it's all good and stuff. But we're just going to take whatever number we get here, we look it up in the F table. Okay, so look up the F ratio, or F statistic, sometimes also known as that. In the F table. And the F table requires that you know two different degrees of freedom. You got to know the degrees of freedom in the numerator and the degrees of freedom in the denominator. Okay, so you have numerator and denominator degrees of freedom. And it works very similar to the chi-square table once you figure out your numerator degrees of freedom and denominator degrees of freedom. Okay, so for the different numerator degrees of freedom, there's a different page. You can just flip to the back of your book. And the F distribution, you can see there's like 6 pages of it. Or even more, 10 pages of it. Each one page for each different numerator degrees of freedom. Okay, we won't worry about that just yet. Okay, so let's try running through ANOVA for this data set here. Okay, so I'm going to just go ahead and erase this. Okay, so let's create our ANOVA table. So we've got between. It didn't tell us how we get the grand mean. I'm sorry. Let's talk about the grand mean itself. How can I calculate the grand mean? Okay, so the idea behind the grand mean is I would take all 12 points, add them up, and divide by 12. But what if you didn't have access to the original data? Okay, what if you know, you're reading some summary thing and they just give you the summary. They just give you the mean of group 1, 2, and 3, the size of each group, and the standard deviation of each group. So let's say they just gave you this summary data. Can you reconstruct the grand mean? Sure, we can, but how do we do that? Yeah.
You could take like 11 times 3 over whatever 9.
Yeah. So what I would do is I would have to reconstruct the grand total of all 12 points. Okay. So I wouldn't just take 11, 15, and 12 and take the average of those three, because we've got to weight these things according to how large each group was. So I'm going to do 11 times 3 plus 15 times 5 plus 12 times 4, and that's going to give me the grand total of all 12 points, and then I'm going to divide by 12. Okay, so the grand mean can be found by doing each group times its group mean, and we add that across all group, and we divide by the total number of points. So in this case I would do 11 times 3 plus 15 times 5 plus 12 times 4 divided by 3 plus 5 plus 4. And then I would get 13. Okay. So let's make our table. So how many degrees of freedom do I have for between the groups? So the number of groups minus 1, so I have 2 degrees of freedom. How many degrees of freedom do I have total? I have 12 points minus 1, so I have 11 degrees of freedom there. And so within would be either 12 minus 3, or the degrees of freedom have to add up, so 11 minus 2, I've got 9 degrees of freedom within. Alright. So let's do the sum of squares. Okay. I've erased it here, but sum of squares between is the fact that each group's mean is different from the grand mean. So I'm going to do y bar minus the grand mean, and I'm going to square it, and then I have to weight that by the size of each group, and I add across all of the groups here. Okay, so if my grand mean is 13, I would do 11 minus 13 squared times 3 plus 15 minus 13 squared times 5 plus 12 minus 13 squared times 4. So that is my sum of squares between, and so this gives me 3 times, what is this, 4? So 12 plus 5 times 4, 20, plus 4 times 1. So I get a total of 36. Sum of squares between is 36. Okay. My sum of squares within, I deleted the points, but I could do, I think it was 8, 16, and 9. So I can, there's a few ways I can do it. I can do it for all 12 points, and I can do 8 minus 11 squared plus 16 minus 11 squared plus 9 minus 11 squared, and then go to the next one and do each point minus the group mean minus 15 squared, add that up for all 5 points, and do this minus the group mean 12 squared, add that up for all 4 points, and add them all together. That would give me sum of squares within. So that's kind of tedious. So we can take a shortcut and just say, if I square this number and multiply it by n minus 1, that's going to give me the that total same number there. So I can do so sum of squares within the original idea comes from each point minus y bar quantity squared, and we add this for all groups, or within all points within a group across all groups, but we can simplify this by saying n minus 1 times s squared. Okay. And so we would do 2 times 4.359 squared plus 4 times 4.950 squared plus 3 times 4.967 squared. And we get 210. And if we were to do all 12 points minus the grand mean of 13, and we squared that distance and we added it across all 12 points, we would get a total of 246. Okay, and that's 36 plus 210. So we're breaking apart the total sum of squares into these two pieces here. Okay, is that alright? So let me just, because I'm going to run out of space. Maybe you guys can fit it all in there. So my mean squares is I take the sum of squares here and I divide by degrees of freedom. So I do 36 over 2. Mean squares is 18. And then over here I do 210 over 9. And I get 23.33. And then finally my F ratio is 18 over 23.33. And I get 0.77. 0.772. Yes.
Can I ask a question about the degrees of freedom?
Yeah.
The degrees of freedom within groups seems a little weird to me. Like, if, let's say there were only 2 groups, and each group had like 1,000 points, 1,000 people in it, versus if there were like 100 groups and each one only had 1, and you would have like 100 minus 100.
Yeah, you can't have a.
And the other one, like degrees of freedom, it seems like it should be number of all points divided by the number of groups or something like that.
So okay, so here we had here I like whatever 5 points, right? And here I have 4 points. So let's just say I took away a degree of freedom for each group. Okay. So within my group, I've got 2 here. So group 1, I've got 2 degrees of freedom here, and then group 2, I would have 1, 2, 3, 4. So I go. So I have 6 so far, and then here I've got how many? 3. So if I take away 1 point from each group, okay. So if I don't count this one for each group, then I would have 1, 2, 3, 4, 5, 6, 7, 8, 9 degrees of freedom. So that's kind of where it's coming from. Okay. So we're taking. So you can think of it as, I don't know, number of points in each group minus 1, and you do it for all 3 groups, okay? but it's easier just to say total number of points minus the number of groups. Okay, so that's where that the 9 degrees of freedom is.
Okay, so when we say within groups, we mean like among all the groups?
Right, right, because we are breaking apart the variance, or the total sum of squares into two pieces. This is the fact that the groups are different, and then the fact that within all of the groups, the individuals are different from one another. Okay, so we're breaking that. So the within isn't just within the fact that the points within group 1 are different, and then we don't have another like within group 2 and within group 3. This is just a within lumping all the groups, saying all the groups are different. Or within each group, the individuals are different, and this is true for all the groups. So that's the within.
So variation attributed to individual differences within all the groups.
Within all the groups, yeah. Okay. And then, so if we wanted to look this up in the F table, we can. Okay, and we would go to the F table with numerator degrees of freedom equal to 2, and we would go to the row where denominator degrees of freedom equals 9. And you use this much in the same way that you use the chi-squared table, meaning you look for this number in between the critical values in the table, and your tail probability corresponds to the column headings there. So, does someone want to tell me what the p-value associated with 0.772 would be? I gotta look this up in a second. Sorry, Tracy. So sorry, it's not actually in the tables that I handed out here, because you'd have like 10 extra sheets in your tables there. But if you look at your book, okay, if you look at 9 degrees of freedom, the smallest number that we have is like 1.93 or something. It's page 629. 1.93, and the next one is at 3.01. And 1.93 corresponds to a tail probability of 20 and 10, and we got 3.01. So 0.772 fits over here. So again, we don't know exactly how much is in our tail, but we do know that it's for sure going to be more than 20%. So my p-value, whatever it is greater than 20%. At least that's all we can say when we're using the table.
Wait, how do you look up stuff in that F table?
So in the F table, you got to figure out your numerator degrees of freedom, which comes from your between groups DF, and then your denominator groups of freedom, degrees of freedom, which comes from the within. And then so you go to that page, and then it's just like using the chi-square table. It's just like using the chi-square table. And you see, look at the column heading, and we see, okay, it's bigger than this, or in our case, 0.772 is less than 1.93. So my p-value, whatever it is greater than 0.20. Okay. So in this case, what would my conclusion be? Okay, do not reject the null hypothesis. And what was my null hypothesis?
All the means are equal?
Yeah, all the means were equal. Okay? So at this point, so my p-value, whatever it is greater than 20%. So even if alpha is 10% or something like that, my p-value would be, I would probably say do not reject the null hypothesis. And the null hypothesis was that mu1 is equal to mu2 equal to mu3. So that the means of the three diets are the same. So we would say we do not have evidence